மணிகண்டன் ஒரு தடவை யூடியூப் ஸ்ட்ரீம் பண்ண விடுவோமா?
நம்மளே வந்துருச்சு நினைக்கிறேன்.
இருங்க, அதான் போய் பார்க்குறேன். எஸ், ஃபைன். இப்போதான் வந்திருக்கு லைவ். லெவனா?
ஓகே சார், ஓகே.
ஃபைன் ஃபைன், அவ்வளோதான்.
மியூட் பண்றேன். Good afternoon, Srinivasan sir. Good afternoon, Anu ma'am.
Can you hear me?
Yes, ma'am.
Yeah.
Srinivasan sir also joined, but his audio is not yet set up.
Oh. I will just ரொம்ப பாட்டு சத்தமா கேக்குறதா?
No, ma'am. Not yet. So far, not yet.
Lavana,
Yes, ma'am. இப்பதான் light
you have the profile with you. Can you pass it on to me?
I have to send to you, ma'am.
Yeah, you can send it to me.
Yeah, we'll send it to you. And ma'am, I have sent that.
Gmail ka?
Yes, ma'am. Gmail. Different.
Navana, you want to ask them to name themselves appropriately?
Good afternoon, Mr. Srinivasan.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, madam.
Yeah.
Good afternoon, sir. This is Lavna from the Paris Program Management Office.
Good afternoon. Good afternoon.
Yeah, she will be reading the questions for us. Are there any faculty, Robin, who have joined?
Dr. Balasubramani has joined from TC.
TC. Okay, I know him.
EC member.
Yeah, I know. He came for our Aspire,
Correct.
I think, right?
Yeah, correct.
It's a challenge to keep in touch with people whom we know. When it's a virtual meeting. Right now,
Correct.
Mari, at least we can recognize him. Who is this TFC 32? Dr. V.
He is the professor now.
He's a professor, right? Okay. Let me stand in the correct location. Actually, I came for an engagement function, betrothal function. I'm sneaking out of that group.
Not much noise.
சாப்பாடு ஏரியாக்கு வந்துட்டேன். அதனால யாரும் வரல சாப்பாட்டுக்கு. நான் தான் first. பெரிய advantage and disadvantage இல்ல live versus virtual.
Yes, sir.
How many people responded to the survey, Lavna?
We'll let you know, ma.
Yeah.
Count, sir. Robin, sir.
From
Morning,
the
you took
morning,
it, no?
yeah,
Yeah.
morning I have taken it. Around 100 plus they have
Oh, it's a good sample.
And before that first set of registration, I think sir might have received from his responses.
Direct response.
Yeah. But anyway, 100 plus is a good sample. What I.
And the registration is also 400.
Oh, I think Tagadagan and the time was the order and they will rush.
3:30 to 3:30 the count will improve.
Yeah. So we are starting at 3 o'clock, right?
Yes, ma'am. Anuman?
Tell me.
Yeah, ma'am. It's 3 o'clock. Can we wait for 5 more minutes, ma'am?
5 more minutes. Okay. 5 more minutes.
Srinivasan sir, do you want to share your presentation, sir? We want to check it.
You want me to share it right away? I will try.
Yes, sir. Okay. Yeah, I will start my share.
Is this from your laptop, or I can do it from mine?
You can do from your side, sir.
Yeah, I'm trying to.
Yeah.
I hope, is this visible to everybody?
Yes, sir. Yes, it's visible.
You have to make it in slideshow. Fine, perfect.
Fine. Hanuman, we have 50 plus participants.
Yeah, you can go ahead announcing the rules and all that.
Yeah, that's what I thought. A warm welcome and good afternoon to one and all gathered here for the PALS Theory to Practice lecture. This is Lavana from the PALS Program Management Office. I will be the virtual host for this event. I would like to mention few basic code of conduct to be maintained throughout the session. First, participants, kindly rename your Zoom display name in the format of college short name hyphen your name hyphen role for our easier identification. Record your attendance in the chat box in the same format which we mentioned earlier. And the third is by default, all participants will be stay muted throughout the session to avoid interruption. Your doubts and questions will be taken in the Q&A segment, and also please feel free to post your queries in the chat box. At the end of the session, we will release online quiz and feedback form. Please watch out for that also. With this, I'm handing over to Ms. Anuradha Ramanujan, PALS champion, for the welcome address. Over to you, Anuman. Anuman?
Can you hear me?
Yes, go ahead.
Yeah, I didn't unmute myself and I was trying to talk. Good afternoon, one and all of you. So, can't hear them saying it back to us. That's okay. Give me a minute, 1 minute. Welcome, one and all. I'm happy that this many people have turned up at this point of time. I hope the numbers will go up shortly. This is not just yet another event of PALS. It's the last of the theory to practice lectures for this year. So we have this very eminent person and friend of PALS. He is also an alumni, BTech chemical engineer from IIT Madras, and the same batch as me, but I was from College of Engineering, Delhi, 1977. He started his career as management trainee in Hindustan Lever, and then he was trained by the best of people there, Dr. A.S. Ganguly and Mr. S.M. Datta, who later became chairman of HLL. And After 9 years of working in the chemical sector, he joined Murugappa Group, where he worked for 17 years in the fertilizer and sugar sector. So out and out, you find his activities revolving around chemical again and again. And he was instrumental in Setica. He then went to Gujarat and he set up a few chemical plants for the Chemplast, Sanmar, and his final corporate job was with Wabag, a water treatment company, and was fortunate to spearhead the setting up of a large desalination plant in Chennai city. So it's a big circle. He came back, and he's currently an advisor in the industrial consultancy and sponsored research department, that is ICSR of IIT Madras, to foster cooperation between industry and academia. He's a true example of what IITians can do to the rest of the society. And he loves to be called as an engineer and introduced as an engineer rather than anything else, like alumnus of this, worked here, worked there, and all that stuff. So who's an engineer? I hope people who had attended RSW will have it in their mind that these are the people who will solve the problems of the world, the knowledge they have gathered as an engineer. So I'm very happy to introduce you this engineer, Mr. M.S. SRINIVASAN, who will give you his thoughts on how to apply theory to real life problems and how do you really apply them in regular when you're in an industry situation. Please, sir, the floor is yours, Mr. M.S. SRINIVASAN. Thank you for this opportunity.
Thank you very much, Madam Anuradha and friends at PALS. As all can see, your true friend always speaks very nicely of another friend. So I'm very grateful to you for your kind words. I also wish some of that was true and nice. Now, as for the students, I really warmly welcome all of you. And I know it has not been the easiest of the times last 1 year. Things have completely changed. I think all of you must really be missing the campus atmosphere, the friendship that you have with people, the classroom sessions that you either attend or don't attend, and of course, access to the libraries where you can refer, and to the playgrounds. In general, the 4 years of your life where you, one of the best that you can ever think of, unfortunately had gone through a very major change. And I must compliment PALS at least trying to help everybody fill the gap by organizing programs like this and helping and motivating you to make the best of the available resources. So that is really a wonderful job. And that is one of the reasons I ventured that if there is any small way in which I can join this wonderful effort, I would be very happy to do. And that explains my presence here today. In terms of about myself, you have heard I am a chemical engineer. I have been trained. And after passing out, I had a couple of options, and I decided after consulting with my own professors at the time and my seniors, and also the people who I held in high respect in family. And then I said, let me straight away join Workline. And you heard that I was also fortunate to have had the guidance of wonderful engineers themselves. So in this lecture, what I thought would be, I would be doing is to share some examples of how applications of whatever we have been taught in colleges could be made use of. So that is what is going to be the thrust of my talk. Couple of good things about that is that there is no mathematics, there is no differential equations, and mercifully there is no quantum mechanics either. So it's going to be very simple and practical, and I hope as enjoyable to you listening as it has been for me living through that. I must tell you, I also know a little bit about you, may not be, each one of you, but as a group. Uh, I must thank that most of you responded, seems, to the questionnaire that was sent. My count, which at around 11 o'clock in the morning I saw, was close to 195 of you have taken the trouble of filling that questionnaire. And this was passed on to me by friends from PAL. So I have some idea. I have not fully studied the entire information, but I have some idea about you. And if I have to capture, here it is. I find that the largest group of participants are from this computer science, IT, and ECE disciplines. Not so very unusual. I think it is pretty expected. So that is the largest portion. There are some from the more conventional branches of engineering, like mechanical, production engineering, and civil. Even fewer are from closer to my domain area, chemical, agro, biotech, and so on. So that makes me wonder a little bit about if what I'm going to share in the next 30, 40 minutes is of use to those from other disciplines. But suspecting that this would be the case, I had tried to make it fairly fundamental and also useful to those. Let's wait and see that. And the second part, which I picked up from the questionnaire, was a question which we had asked about your intention and plans of what do you want to do after you pass out. I think most of you are probably in the second, third, final years. So you would naturally, as expected, most of you, I think more than 75% had said that you would be really looking for jobs immediately after passing out. There are also some who have said that you would be interested to pursue further studies, either in engineering disciplines or in management studies, both in India as well as abroad. So that's very nice. So some of you have ambitions of improving your qualifications. Now, and this is the third question, which is the most important question that as far as today's topic is concerned. We had asked you, saying if you are looking for an entry-level job, which means your first job in any company, what would be the predominant factor for you to make a choice? The usual suspects are, if there is a very high salary, if there is a company that offers you a job which is fairly close to your hometown, and so on. But overwhelming number of you had given the answer as what you would be really looking for and valuing in your first job is a learning opportunity that you consider as very important. Now, this is very nice. And as a person who have been watching young people for close to 30 years now, you are very typical. I think at this stage of your life, when you are in your early 20s, the one thing that makes a lot of impact on each one of you, which you attach importance, is in the job, you want to have opportunities for learning. So that's very good. But I will come back to this theme of what exactly is the learning opportunity. This was actually one of the questions that was asked. If you had chosen to say, I'm looking for learning opportunity, there was a supplementary question, sort of, which said, what exactly do you mean by learning opportunity and why? Why are you looking for learning opportunity? And here, of course, the answer was not a multiple choice. It was free text. Therefore, it's very difficult to summarize. But I'm going to make use of that as we go along. So hold on for the present, that this is very nice. So the topic today is part of this. Apparently, this is the final lecture of this theory to practice sequence. So, presumably, you have had other illustrious speakers tell you about the theory part and how that theory is going to be helpful to you in later on in your life. Anybody who ventures to do that makes two broad assumptions. The first assumption is about what is likely to happen in the future, which means by the time that you pass out and join your jobs, then you aspire to grow in your jobs in terms of a career. What is likely to happen in general to the companies, to jobs, to industries? You have to have some forecast made. That's step number one. The step number two is also what is going to be your role in any given situation. Both are, I think, are extremely difficult to do. One honestly doesn't quite know how the future will unfold. All we have to do is to look at the number of projections that have been made and mercifully forgotten for so many years. Every time when a new wave starts, people say in 2020 this will happen, in 2035 this will happen. We don't go back normally and check what was promised in the year 2000 when we were in the early 90s and what really happened, or what was promised in 2020. In fact, one of the famous slogans in those days was poverty will be driven out by 2020. And it will be worthwhile to go back and see what is the present status. So forecasting about the future trends of industry, jobs, etc. is not very easy. Even more difficult is the fact, what is your role going to be? Because like I said, I notice here people are a mix of specialties, largest being computer science and IT to biotech and so on. So your role of any company that you are going to join, how your skills, what you have picked up, what your knowledge gained, and what is your internal attitudes is very hard for somebody to predict. Therefore, summary is, in my view, it's extremely hard to give a very satisfactory descriptive answer to this question of how the theory is going to be used in practice in the future. I have taken the easy option of telling you what has happened in the past. The hope is that some of these past lessons could also be useful to you in your future as it evolves. With that brief introduction, let me go a little deeper and tell you a few what might seem as general statements, but these statements are extremely powerful and extremely long-lasting. Engineering education is based on science because we are not empiricists, which means we don't have black magics and snake oils for problems that we face, but we believe that we must base our solutions on well-documented and well-proven scientific principles. So science is the starting point of our engineering education. And then if you look at the scientific education itself and how our education system is worked, fundamental to that is the ability to observe natural phenomena and draw conclusions of the underlying causes. I think most often quoted example was that of the father of mechanical sciences, Sir Isaac Newton, who saw an apple falling apparently and then said, okay, this explains the motion of the stars and the planets in the sky, both being governed by gravitational forces. So observation is the starting point. So in our studies in education, in the 4 years that we rush through in colleges, we depend on other people's observations because a person's observation is limited to his lifetime and his senses. On the other hand, taking advantage of hundred thousands of other people's observations and their analysis, we have got codified scientific principles and engineering principles. But let's not forget that it all starts with observation. The second part of our engineering education is apprenticeship. And this was true if you go back to even medieval recent times. A good engineer began his career under apprenticeship with another senior craftsman of the same trade. So this meant that after our observations and codified knowledge, in order to be able to take a new situation and then apply your knowledge to that, you needed the input of a person more experienced in helping you interpret the reality. So apprenticeship was the second most important part of engineering education, first being observation and science. The way it is structured, if you read back, is because what is the purpose of our education is in order to help everybody to be able to predict the outcome of a situation, and therefore you are not left to guesswork, but you can, with some confidence, predict how things will work out for a given situation that faces you in life. So observation and apprenticeship, that was supposed to be the basis of our education. However, sometimes, somewhere, I think this thread is getting either forgotten or loosened. Now, why do I say that? At this point, I must give you a very popular joke that goes on in the Department of Physics at the University of Chicago. As some of you know, University of Chicago Department of Physics has housed doyens of physical sciences. Who is who in physics have all started their career or worked there for some period of time. The popular joke about the department is, if somebody went and told them a certain phenomenon happened regularly in practice, they would say, that's all right, that is fine, that's in practice. But how does it work in theory? The logic being, a strong physician is one who has an explanation of why things happen. So that was the joke about the theory rising out of practice. So in this talk, therefore, I would summarize and say, probably what we should be doing is not theory to practice, but theory and practice, because your life, you will continue to learn, as most of you have already said. And the observations, the context of the observations will also change. Therefore, it is a kind of a feedback loop, both of them going together. This, I think, is, I have a concern here, particularly for fellow engineers like you and me. I notice that as opposed to the other professions that we all know, medical, for example, medical education, lawyers, accountants, for recent meaning last 10, 15 years of engineering students, I had found that there has been decreasing exposure to real life situations. And therefore, the transition of after passing out and then entering your work life and there trying to apply your knowledge, observations, and practice becomes harder. Also, there have been newer areas of teaching which has emerged. I think computer science itself is something which is, I can say, is fairly recent in terms of being taught in classes and things like that. So it is but natural that some of you would feel not so very confident when you take up your first job, saying, this job seems a bit daunting and how do I tackle it? So here is the way forward, is what I would like to share with you. First, when you join your first job as an engineer, what will you do is what we need to understand. Now here I quote my learned professor M.S. Anand. He said that engineers make things that God forgot to make. I thought it was very powerful, very motivating. Just look at the number of things that we take it for granted, right from the time that you wake up in the morning until the time that you go back to bed in the night. Just run this in your minds. You wake up, reach for your toothbrush and paste, then you make coffee for yourself. There are a variety of juices available in the fridge, refrigerator itself being an innovation, and so on. So every one of them has been made and perfected by engineers, team of engineers, to be honest, like you and me. But the catch is, unlike God, who made most of the things free of charge, things and people and company cost, and they charge you. This is where the difference. So what engineers do is probably they make the things that God forgot to do, but they have to make it at a price that customers will buy. They have to make it at a cost that is economical for the company that engages. So straight away we come into two other concepts which are not usual engineering teaching. So what we should learn, of course, I think I went through also the Chennai University or Madras University or whatever it is called, university's course content on pre-tech for various subjects. I think in the first 4 semesters, almost all of us, irrespective of the branches that we are in, are taught the fundamentals of physics, chemistry, mathematics, obviously, and in some places biology. I'm not sure, but biology is increasingly a common subject for all disciplines. These are the bedrock fundamental principles of science. And then the usual engineering subjects out of this are what I have listed down here: strength of materials, fluid mechanics, electricity and magnetism, chemical kinetics, thermodynamics, what have you. Now, the largest population of the students present here may say, why have you forgotten to add things like database structures and algorithms and things like that? And that, of course, 2 reasons. One is the fact that I am ignorant, being a chemical engineer of olden days of this subject. And secondly, the examples what I'm going to give probably more relate to the old school of thought. So I have not added, but you might add those principles. So this is the first set of scientific and engineering principles. The second set of principles, like I said in the last slide, is economic principles. Sometimes it is taught, I think, in your coursework, but that's not a worry. Most of us experience it every day. I mean, including those who don't go to college, experience economic principles. Therefore, student engineers, if they are aware of these two, then I think your work will become easier. Moving on to, you would have certainly had some expectations, I hope, when you registered for this, as to what you can gain by attending this talk. Now, that depends on, in my opinion, why you chose, first of all, to study engineering. This was not part of the questionnaire, but I think most of you probably did because someone influenced you in the family saying that if you studied this, this will be good for you. And some of you also felt that, yes, that makes sense, because if I take that engineering subject and engineering course, I'll probably get a much better job. And therefore, my career, my standard of living, everything becomes better. And some of you might have even taken a liking as you started reading to the subject. So again, these two are linked to the fact that, partly economic principles and partly understanding of the nature. Now, while unfortunately this talk probably will not help you in how to get a good job or how to even to get a good internship, it might certainly help you, in my opinion, that after you get the first job, entry-level job, from there, how to build your subsequent career and lead a satisfactory professional life. I'm very sure that this talk will help. Believe me. How? Let's go with some examples. I skipped the earlier slide because it basically said the kind of a job that you can get it. So what is of most important for this talk is, I think I will focus only on companies which are run for profits. So for-profit companies is usually most of the companies, excepting rare organizations which are like PALS serve community. With rest of the organizations that we know of, where you are likely to begin your career, are those who want to, at the end of the financial year, make more than what they have spent. That is what is for-profit companies. So if you want to first join a company, you have to be very clear that the objective of the company at all times is going to be that whether they are able to, in their activities, make a profit, make money. And therefore, your role, your career, your work will center around applying your knowledge, observations, and skills to furthering company's requirement, which is making profits. Now, of course, I'm saying that profits in a very, very economical sense, not with any connotations of either it is good or bad. It is, in my opinion, that all of us would realize over a period that a well-run company can be run with ethical standards and with complying the legal requirements of the country, but nevertheless has to make a surplus for it to be able to continue to serve the customers and, of course, pay its employees. So this is absolutely a must. Probably it is just stating the obvious, but since there are views and opinions about it, I thought I would just mention that. So if the company in which you are going to join, for-profit company, is basically one where all efforts are made to use the combined knowledge of the employees to make a profit for the company, obviously your role, and especially your role over a period of time, right from entry-level job to building up a career, should be around the question of what you can do to use your knowledge for the situations that the company faces on an ongoing basis to benefit the company. Now, let me stop here and then remind you of the survey where you said what you are looking for in an entry-level job in a company. You are saying you are always looking for learning opportunities, right? So that is what I heard you say. Now, I draw your attention to the fact, while that is probably your expectation, the company's expectation in hiring people like you is not exactly to provide you with learning opportunities to satisfy you for whatever reasons you are wanting to learn. But their most important requirement is, of course, is to ensure that the company is run in an efficient and profitable manner. Is there a conflict between the two? Is what one has to think about. Probably not, because if we accept that in our day-to-day life, when you are in a family, in a group, so on, we are all the time meeting group objectives while trying to live harmoniously with each other, can extend itself to the fact that you can still continue to work for a company, meeting the company's requirements, at the same time also enjoying your professional career, because in the process of applying your knowledge to the company's benefit, there is a lot of learning, and of course there is a lot of gains also. When the company gains, you gain. So that is the transformation, to my mind, is most central when you take up a job for a company. And those people who are able to adjust and accommodate to this quickly enjoy their career. Some people find it very hard because they have not been able to make the transition from what is there in it for me stand to what is that I can do contributing with my knowledge. And that is something that it is worthwhile for you. And this is true for whatever branch of engineering you are. Next couple of slides, I will give some practical real-life examples of how engineers of various disciplines and backgrounds have actually done it to benefit and therefore, also gain. I think we discussed this very, very clearly. The important point I want to maintain is, since your career is long, as I showed in the earlier slide, it is advisable to retain your textbooks. I noticed this many times when we interview youngsters. When you probe them a little bit on the subject matter, it is natural that the interviewer is more knowledgeable, is more experienced anyway. Therefore, it is possible that he knows more than you in a given area, which is fine. And no one is really looking for Albert Einstein to be recruited. But however, what the interviewer is looking for is your willingness to stay connected to your fundamentals. Therefore, it is worthwhile retaining your textbooks and not sort of decide that once you pass out, they are no longer required. It's absolutely required. Fundamental books are absolutely essential for you as a reference guide in our long career if you choose to become an engineer. And you must also all the time by looking at cost benefit analysis. What we are told in colleges, in subject studies, is the analysis part, how to solve a problem in technical terms. Whether those problems solved in that manner actually is going to benefit somebody else is where the cost benefit comes. I will do this by some example. So keep that cost benefit very clearly in your mind. Now, we have been talking for nearly 25-30 minutes, so some slight diversion to refresh our mind. I know there are civil engineering friends here. I think there is 15 of them have been registered. I think this course, you will find it very interesting. The following two examples. This picture, some of you might know, this is a place in Western England, place called Stonehenge. Apparently, this structure of stones standing in some semicircular pattern had been put up close to 3,000 years ago. There are a lot of speculations as to why people went to the trouble of setting it up, but it's a very big tourist attraction site. People go and then wonder as to how this was achieved 3,000 years ago, especially considering there are no known sources of such stones close by. Samples of the rock have been found, and then such has shown that the nearest source of rock had been 200 miles away. And there are questions of how it was mined, how it was transported, brought to the site, how this site was selected first of all, and then how it was, erected up. So this is 3,500 years ago. More to our Tamil Nadu here. I think this, most of you cannot miss this, what it is. Yes, it is the big temple in Tanjavur, built during the 980 to 1010 Rajaraja Chola's period. One marvels at what has been achieved. Again, this was the period where there were no internal combustion engines to power movement. There were no cranes, probably because even Sir Isaac Newton came into being only in 1642. So, and look at the way you wonder whether these structures were prefabricated somewhere and lifted and placed, or the large structure was put and then, people went to work in carrying out this wonderful architecture there. So this is another thing, what has happened. Of course, there was a lot of knowledge used. We do not know exactly how it was done in both cases. This is lost. But one can speculate. There are a lot of speculations about how it was built. But the point about this, as it is relevant to our course today, is that here was an objective. This objective was decided by the king. He decided probably that I should have one of the largest granite temples built. And then engineers built it for him. The question of cost benefit, the budget, the efficiency, the price did not arise in that context. So compared to that, a typical engineer's job today is probably not as grand as this, but certainly equally challenging, because for you, whether you are involved in making a refrigerator company, or you are involved in making a television making company, or you are involved in a chemical manufacturing company, or you are going to set up your own business, for instance. All the time you have to take the second advantage of applying your knowledge, but in a cost-effective manner. Okay. Let's come back to year 2000. This is an example from the chemical process industry where I am very familiar with. This industry made something called phosphoric acid. Now, phosphoric acid is an ingredient that goes into making of phosphatic fertilizers. Some of you who are either into agro or have families with the agricultural practices will know DAP, diammonium phosphate, is a very popular fertilizer, and it uses a large amount of phosphoric acid. So this is an industry which made phosphoric acid, which was subsequently converted to phosphatic fertilizers. Now, the process of making phosphoric acid was, you have something called a phosphate ore, which is mined. In India, we do not have adequate resources of phosphate ore. So almost all of the phosphate ore that is used in our country is imported from Middle East. And then this comes, it's a solid, fine. It absolutely looks like sand. I mean, that's it. Then it is reacted with sulfuric acid. I think some of you will remember it from your chemistry classes. Sulfuric acid is a very corrosive acid. So that is a liquid. So there is a solid liquid reaction that takes place between phosphate ore and sulfuric acid. What you get is another set of solid and liquid. The liquid in this case is the required desired phosphoric acid, and the solid is called gypsum, which is the byproduct. So one solid and one liquid reaction transforms to another solid and liquid. Now you need the phosphoric acid for conversion to fertilizer. So this liquid and solid have to be separated. And you obviously, the common equipment is the filtration. You just filter and remove the stuff, take the phosphoric acid to use. Now, imagine you and all of you for this example become chemical engineers. So you have studied chemistry, you have studied physics, all that pandas. Then you have also studied a little bit about thermodynamics, whatever I have shown. Now you join into the company as an engineer, and then the company is seriously looking at and saying, what is their need? Their need is they want to increase the production of phosphoric acid because fertilizers are getting sold nicely. There is a good demand. Therefore, your company thinks that if they are able to make a little bit extra production from this plant, they would be happier. And therefore, you have joined. You are asked to join the team. Then say, why can't we all sit together and find out what are the ways and means of making more production? So that's how typically problems in industry start. Either to increase production or to reduce the cost, or in some cases improve safety, use of convenience for the customer. So with a problem, we start. At that time, the problem is not defined as a mechanical engineer problem, it's a chemical engineering problem, it is an electrical engineering problem, it's a computer science problem. No, it's a problem for the customer. Now, the team of people of multi-disciplines, when they join together, they have to break down the larger problem into smaller ones, which have to be attended to. In this case, how it was done was, if you want to have more production, there were two ways of doing it. One is, if the plant had a certain capacity of turning out every day, what I call as tons per day, you can try to see whether that can be pushed up. If they said that in the past the plant had been producing 100 tons a day, for example, you can figure out why is it limited to 100, why not 105? I mean, we are not talking about 200 here, even 105, 110, a little bit extra. What is preventing it from making extra? Of course, taking into account safety, taking into account legality, ethics, all that. The second way of doing it is, it's fine, it is producing 100 tons per day, but in a year, there are 365 days. Does it run all the time? These plants are continuous process plants, or does it stop in between for whatever reasons? Breakdowns, this, that. Running time, what I call as on-stream factors. So this company analyzed both, and then the group of engineers said what they would do, because increasing the per day capacity means major equipment modifications and things like that. It can be done, but it's a bit, again, cost benefit, more expensive. So let's look at so-called low-hanging fruits, things that can be done within a short period without too much of expenditure, but in a very reliable manner. So that team chose improving the running time. So they went through the records, first of all. What is the current situation? We said in a year 365, 24 hours a day. What is the actual number of running hours? They looked at the records. These are called downtime records, meaning when an equipment is not running, it is stopped for whatever reason. The reason for stoppage and the number of hours or minutes that it has been stopped before it was put back online is recorded. So there was a data analysis there. So there is somebody who did that data analysis in terms of frequency, highest contribution, and severity, all that, whatever statistical analysis was done. Then we also went back and said it stopped all right, and this is the major reason for the stop all right. But why did that happen? There is an ultimate underlying cause. Going back to the fundamental, right to the fundamental, scientific principles, observations. If there is a stoppage, what caused that stoppage? So this is again takes a lot of thinking, analysis, and absolute fundamental analysis. And then once you understood what the cause is, suggest solutions for overcoming the cause. Try it out. Put it in a small place and then see whether your logic is correct. Test. So that was the logic adopted by the team. Here is a sketch of that equipment. You can see two circles, F and B, and C and F. This is F is called the feed end, and C is called the chute end or discharge. These are two rollers. You can see the cut section of the in the map. So these are two rollers here which are rotating, and the black thing that is running along is a very specially designed belt. So this belt runs here like this, from left to right. It is rotating. And top of the belt, you have this green stuff, where this, remember in the slide I mentioned about phosphate rock and sulfuric acid reacting to form another solid and liquid, phosphoric acid and gypsum. That slurry, which is a mix of solid and liquid, is brought here and added at this feed point. F. So it falls and then it travels like this, comes down, and then at the end of it, the solids are dropping out. The idea is from this time to this time, the solid and liquid get separated through the belt. So the belt is a very specially designed belt. And on top of that, there is a fine cloth, polypropylene cloth. You can see this, what is shown here, the pink thin line. This rides on top of the belt. So actually the solids are formed on top of the cloth, and through the cloth, the liquid oozes and goes into the grooves of the belt and then gets into the blue zone. So that's how the liquid gets separated. The solid comes out and drops off at this point. Now these stations here called PPB are those where you don't want to waste any phosphoric acid. You know, some of you who have seen coffee being made, decoction coffee, you take the coffee powder, roast it, grind it, then add hot water to that. You get the first batch of decoction. Still, there is some stuff left in it. Right? And then you can put some more hot water into it, and then you can get a second slightly diluted coffee. Similar principle here. So you don't want to lose that phosphoric acid. So even after the phosphoric acid is separated from the belt, you add water and phosphoric acid dissolves in water, and you wash that cake so that the cake becomes free of phosphoric acid. That's in principle. The rest of the setup is, as it falls, there are nice compartments through which it is collected. These are receivers 1, 2, 3, 4. And there is a principle in chemical engineering. It says it's a counter current operation, which means what you do is that to get as pure product as possible, the last product, you must wash it with the purest water. Take an example of our own washing machines. There is the last cycle is where you really put fresh water, and that fresh water removes all that. Then the water that is getting collected in the washing machine, you don't recycle, but in the olden days when you used to have buckets, people can use that water once again like that. So that's the same principle. This is the water, clean water that comes in. It washes the cake, falls, comes, gets collected in this. Then using this pump, it is pumped back again. You can see it goes upstream, falls back again for washing this cake a second time. This wash is for washing the cake in this portion. This wash is for washing the cake in this portion. And this gets collected into this container. Again, it comes back for a second pickup. Out it goes into this. It comes here and then goes somewhere else. These two, what are they? This is the final version of the solution given by the engineering team. But this is actually where the slurry falls product. Gypsum starts separating. This is the most concentrated acid that comes down. This is the product acid, phosphoric acid. And this, which is the second concentrated, this has to go back to the process again so that it gets further in. So basically, water starting from here goes through cycles in the belt. From here, it goes to the process, and from here, it comes out as phosphoric acid. And as you know, in order to do filtration, you must have some either pressure applied to make it happen faster. So this pressure is applied as reverse pressure in terms of vacuum. So if there is a vacuum pump, the green stuff on the left-hand side corner, you can see this pump. This applies vacuum to the separators. They in turn apply that to the belt and the cloth. And that's how the fastening of the rate of filtration takes place. So this is the cross flow diagram. What was this? I will skip. When we analyzed, the team's idea was, is this running all the time? It was found that the pumps had been failing very frequently because they get blocked with fine particles of gypsum, what is called as sludge. So go back again to this. Like these two pumps, the original design had a pump here and a pump here. This pump was to pump it into a phosphoric acid storage tank, product storage tank. This pump was to pump it back into the process. The problem was first in these two pumps because this is supposed to completely separate the solid and liquid, but there is nothing called complete separation in life. So there used to be some amount of solids coming along with the liquid. They slowly started building up in these two blue vessels, and the leg of the pump was getting blocked. So after some time, this pump won't pump anything else, which you can see when the process gets upset. You stop, you clean, and then put it back again, and it starts. So this was one major cause of the downtime. And in general, of the 1, 2, and 3, and 4 pumps, these two pumps were the ones that were suffering a lot of downtime. So that was what is the data observation. What was done? The winning solution. Several solutions came. Then someone asked that question, saying that, why do you need the pump? That was a fundamental question. If you did not have that equipment, of course, it cannot fail, right? That was the logic. So they said that, okay, if you don't have the pump, how do you, for example, if you don't have this pump, how do you get this liquid going on top of that? This is under a vacuum. So from the bottom, it has to go to top. How does it go? Sorry, can't be done. So we left it. When it came to these two pumps, the thing was, this equipment was actually located because of the vacuum requirement at a height of almost 14, 15 meters from the ground level. This entire piece of equipment was located at 14, 15 meters. Unlike these two, where the products from here have to go to the top, this had to go back to a reactor, which is at the ground level. And this has to go to a storage tank, which was also at the ground level. So somebody asked the question, okay, we need these two pumps because if we don't have the pump, the liquid will not go up. But why these two pumps are required? Then detailed calculations, fluid dynamics calculations were done. Then after doing the fluid dynamic calculations, it was found that by modifying the pipelines, you can eliminate these two pumps and adopt gravity flow. This was actually implemented. And the two pumps which were eliminated were made as standby pumps for the other two pumps. So that in the odd chance one thing fails, you immediately switch on to the second pump and restart without having to stop the plant. This improved the productivity of the plant considerably and resulted in the production from the plant going up very significantly. And actually this plant, after 2 years, because of the consistent performance, won the best phosphatic plant award for the country. So that was the crowning achievement. Go back and then see what basic principles were used, theory to practice, and who applied it. Now, this was done by a set of engineers under the guidance of the operators who operate the plant. The operators were very clear about the conditions prevailing in the plant, so their knowledge was very useful. The engineers who came with the basics of filtration, with pumping, pump flow, characteristic curves, pressure loss, pressure drop, fluid mechanics, scaling, that kind of a principles when they joined together and applied, generated a solution, and the solution solved the problem in a very cost-effective manner. So that was one example of how engineers are. Now it's 4 o'clock. I can continue to give an example for electrical engineers. It will take another 15 minutes. Is that okay?
I think we can go, sir.
Yes, just 15 minutes, so that I do justice to the other branches of engineers. Now, I came out with the example for electrical engineers, and electrical engineers is one of the hottest topic today is renewable energy, and what role renewable energy is going to play is certainly going to play some place. So this example concerns best utilization of renewable energy under a very specific conditions. Now, normally renewable energy sources are wind energy, wind turbines, and solar PV cells. Okay, both of them are seasonal. In the case of a wind turbine, of course, there is a particular season of the year where the wind velocities are very high, and therefore you get production from the wind turbines. The rest of the year, it is due to very low velocities, it is not produced. Whereas for the PV cell, it is a daily stuff. I mean, as the sun rises around 8:30 in the morning, the solar flux increases, reaches a peak around 12 to 1. Then by 4:35, it drops. So the solar panels are not constant power producers. Their power output varies with the time. And if there is a passing cloud goes by nearby, then of course there is a sudden drop. So the renewable source of power, in summary, have one disadvantage, which is their variability with the time, either during the short duration or during the long duration. On the other hand, users of power do not want variation. Who wants the power off or low voltage when you are watching a cricket match? So there is a balancing that you have to provide by the electrical distribution setup of accepting varying supply situation, but ensuring that the demand is met. Now, even demand varies for that matter. For instance, when the summer comes, everybody likes to sort of beat the heat by turning on the air conditioner if there is one, and therefore there is a peak. So on the demand side also there is a variation. There is a supply side also there is a variation, and therefore it is helpful to have an intermediate storage which acts like a buffer. Now, this is how is it done? Increasingly, it is being done by means of batteries, large battery storages. And the battery storages that all of you have heard about, which is competing for the market, is lithium-ion batteries. These lithium-ion batteries act like a buffer, that when there is a large production from the renewable sources, more than the consumption, you get the batteries charged. Then when the reverse takes place, you can get these batteries to discharge. So that's the concept, that's the theory. Right? In practice, there are some difficulties. The difficulties are, in a battery, lithium-ion battery especially, you can have large capacities by putting more number of batteries in terms of kilowatt hours. But if you want instantaneous demand, which is power, kilowatt rating, this struggles. I hope it is clear. So batteries are all right if there is a very slow change in the demand, with a slow change in the generation, you can get by with the lithium-ion batteries, hopefully. But in reality, the demand increase happens sharply. Similarly, the fall in generation also takes place fairly sharply. So the battery would have to rise up to the occasion of delivering high power requirement, instantaneous power requirements. For this, a recent development is something called a flow battery. Let's see what this flow battery is. Here is a sketch. This shows one cell of a flow battery. Normally, it is a battery of all this continuously put together, but I have just for developing the concept, tried to show you a single cell. There are two things, electrodes, one with a plus sign, the other one is a minus sign. These are electrodes through which electricity enters the cell or gets out of the cell. As when the cell is getting charged, electrons enter, and when the cell is getting discharged, the electrons flow out. So that is the two electrodes. Then there is this wavy stuff. This is a very specific type of a membrane. This property of the membrane is that it will allow only hydrogen ions to move through across. All others are blocked. So that's the kind of a specific membrane. Like the membranes of our own body, in the kidneys, they filter water and not any other proteins or salts, usually. This is a very specific type of a membrane which has been synthesized, which allows only hydrogen ion movement either way, but no other ions. So that is the membrane. And there are on this side one electrolyte, and this side another electrolyte, shown two different colors. And two large compartments to capture the electrolyte, store the electrolyte. And I don't know whether you can see in this, there are two pumps also here. This circulation is maintained by one pump, and this circulation is maintained by another pump. What happens is that this chemistry, now okay, I will now switch to the chemistry and then come back to this. Yeah, this is anode, cathode. Let's skip this for the rest. This is the chemistry. This is the membrane I have shown here to show that hydrogen ions can go. Hydrogen ion crossover is shown. This is under the condition where electrons are flowing into the cell, which means the battery is getting charged. There is an external source through which electrons are flowing into that. So there is this compartment, and then there is this compartment. In this compartment, what happens is the electrons, when they enter from the electrodes, they jump to the solution. And this is a salt of vanadium. Vanadium is one of the elements, I think in periodic table you will remember. One particular salt of vanadium. Vanadium has an interesting property, again, going back to the basic sciences, is that all of you have heard about oxidation potentials. If not, please don't throw away your electrochemistry book, go and read it again. There are standard potentials for reduction and oxidation, and different materials at different oxidation status. Vanadium has several oxidation states. Now, in this case, the V3+, which means vanadium in 3+ oxidation state ions, pick up those electrons, become vanadium in 2+ oxidation state. There is a reduction. As you know, gaining of electrons is oxidation, is reduction. And the H+ also, which is oozing across the membrane, also picks up the electron, and this V2 to V3 hydrogen gets added to that. So there is a reaction that forms. Now, electron came from somewhere, but we have to know where it came from. This comes from this side, where there is another salt of vanadium, which is releasing electrons. You can see from here, oxygen electron status is -2. So if overall, if VO2+ is there, this oxygen is -2. Overall is 2+. Therefore, vanadium has 4 oxidation states. Whereas here, if you see, this becomes 3 oxidation states. The reverse of this takes place in this case. So the electrons flow from here to that. This is during the time when the battery is getting charged. When the battery is getting discharged, the reverse takes place. Now, this potential difference between the anode and the cathode is approximately 1.7 volts. That's the chemistry. This chemistry has been discovered in the lab. Now, go back to our problem. All this chemistry is fine, but what is that we are trying to do? We are trying to find how to gainfully utilize renewable energy excess in order to store it and also able to draw it in a very fast manner. So that was the requirement, right? So just a picture again, then we'll go back. What basic engineering principles are used in this flow batteries? These flow batteries have now come into market in the range of 3 megawatt, 4 megawatt size. So that is the kind of present development. Now, the beauty about this battery is you can draw large quantities of power out of it. For example, a typical 5 megawatt battery can discharge at the rate of 5 megawatt. Now, this is huge, humongous. Whereas no amount of conventional batteries, you will be able to draw that kind of power. Those of you who have tried to start your car on a cold day, or you first attempt you make, the battery doesn't, the engine doesn't fire, then you are supposed to give some time before you make the second attempt. Because if you try too many times, the battery runs off, and then you have a dead battery, you are stuck. So the conventional batteries have this limitation, inherent limitation, whereas a flow battery does not. How did we overcome this? What is the basic principle? The basic principle is inside the battery cell, single cell, in a conventional battery, there are ionic movement from anode to cathode in order to complete the circuit. Recall, when we talked about this, electron flow, is very fast. Whereas electron flow doesn't stop. There is something happening inside the cell in terms of the electrolytes and so on. Here, ions diffuse. Now, in a conventional battery, ions, as you know, these are metal ions. Electrons mass, some of you who will remember that mass as 10 power minus 19 kilograms, around that, compared to the mass of the atoms. Atoms are way beyond bulk. Therefore, the diffusion to reach from one place to another place, you are asking a sumo wrestler to sprint a 100-meter race. So that is the fundamental reason why the conventional batteries are not able to give you an instantaneous power kick. On the other hand, here, if you have noticed, the ion movements involved are hydrogen ion, which is probably the smallest known element, H plus. So therefore, the ionic movement of hydrogen ion is much faster. Added to that, there is a second, which is what I have called here, is mass transfer coefficient across the electrodes. What is this high sounding mass transfer, excepting for chemical engineers? Here it is. Yeah. So hydrogen ions going through this is one part, but electrons and the ions will have to react at this electrode surface. So electrons has come here, the ions can go here. At this stage, because of these pumps, and they remove those formed ions very fast and pump it out into the storage tank, there is a much faster movement of ions, and that results in higher current and therefore higher power. So that is the basic principle of this redox battery. Now, by making these two tanks as big as possible, and by connecting several of these in series, you can get the voltages that you desire. And finally, this is the DC voltage, which is converted to an AC voltage and then connected to the grid. So that's the basic principle of that. Here again, what the engineer's role is, first apply the principle. And there are lots of engineering challenges that we have to solve. Remember, the second leg of our horse is cost benefit. Now, why would anybody want? Okay, if somebody wants a very high power starter, why would he want that? And secondly, finally, this is of course an expensive piece of equipment, definitely. And how does anybody pay for it? The cost benefit comes along from two factors. One is you are doing this because you can store renewable energy. If everything was connected to a thermal power plant, 500 megawatt thermal plant, these thermal power plants operate in an absolutely steady manner. Now, when the demand comes, they have what is known as a gas turbine. Because this thermal power plants, what you have seen if you travel around, can't be easily started and stopped or adjusted. These are monsters. You can't just have it, 8 o'clock at 1000 megawatt power output and 8:30 as 800 megawatts like that. These have to be operated at the steady state conditions. Whereas gas turbines are much compact, more expensive, but much compact equipment. They are the glorified version of our aircraft engines. In aircraft engines, by the time you take off, in that 5 or 6 minutes, amount of thrust that you can develop is very large. So this is, of course, connected to a stationary power source, and you get instantaneous power. So usually, currently, a combination of gas turbine engines and power plants, and also grid connectivity with other grids. Because sometimes the Tamil Nadu grid may have a high power situation, whereas our neighbors may have a surplus situation. By grid management, you can import power from there. So that is what it is currently being done. In that context, if you are an electrical engineer, if you are able to come out and then say, I can accommodate more renewable energy power so that either I don't have to import power from my neighboring state, or I don't have to run the gas turbine with a higher cost power to meet the demand, then the equation works out. So that is the second leg on which engineers apply their mind and decide. Okay, I think I will now conclude here. Basically, the message is focus on your basics, engineering and scientific principles. Honestly, there are only a few of them for all branches of engineering. Whichever branch you choose, the first 4 or 5 semesters, what you are taught in terms of basic physics, chemistry, strength of materials, thermodynamics, they are the fundamentals. Rest comes by empirical observations to a given situation. So keep your focus on the basics. Second is look for opportunities in your actual work context. Opportunities, again, for learning is what you are all looking for. I appreciate that. But apart from personal benefit of learning for you, look for opportunities to contribute to the company's goals in terms of increasing production, in terms of reducing the cost, increasing safety, increasing reliability, whatever. Some parameter which has a lot of positive influence on your employer, you have to look for opportunities. And then if you did a combination of your basics to the job opportunities for the company, you have a career going. Like somebody said, a career is not a sprint. It's not that every day you do something. It's a long, steady climb, but it's very satisfying. This is, I really have to point out to, I think most of you are from Tamil Nadu, but there may be some young students who are not from Tamil Nadu. There is a wonderful piece of literature in Tamil called Tirukkural. This is 2-liners, 1330 of them, a couplet of 2 lines on various subjects and various topics of human life. It's wonderful to read, and there is also English translation these days available. So I picked up one of them to leave the thought with you. In Tamil, it reads as Epurul Yararvai Ketpinum, Apurul Meipurul Kanbadu Arivu. English, for those who do not follow Tamil, is your objective should be to discern the truth in everything by whomsoever spoken. That is true wisdom of an engineer. And the truth comes from applying basic scientific known principles to a given context in order to meet the objective of your employer. So that is what I will leave the thought for you to go through. I wish you all success. I know that last year has been an extremely trying, unusual year. Opportunities for internship probably are not as good, but I'm sure things are picking up and things will change. And I send you my good wishes for whichever career you choose for success. So I would stop here and hand over back to the organizers for taking it from there. Thank you.
Yeah, thank you so much for the wonderful session. So we have received a few more questions earlier for this session, and we have covered most of them in the session. So these are some of the questions. Do you want to add on this too?
Yes, let me read through that. Okay. The first question is how to relate the design into practical design process. Now, the fact you have brought that practical design means something is there in your mind, right? As you are taught in the class a design, then you will be told the principles. Let's say you are designing a structural member for carrying a certain load. So the first principles you go through, do some calculations and find what is the members of the load bearing member, what is it subjected to stand in terms of either compressive load, tensile load, or bending moment, or shear stress, or a combination of shear and torque, whatever. So first would be to visualize the application and derive at these loads, and then use known principles. In this case, of course, allowable stresses for that member for the given material, and find out what is the dimensions of the tail. As simple. This is what is we are taught in the class. Now, when you say this design, how do I take it to a practical design process? What is practical will be so very different from everybody's life and everybody's situation. If you are in working for an automobile engineering company, and they came back and told you that in one of the models of the car, there is a frequent failure of the bearing of the crankshaft. Now, you will have to first understand, probably you don't even know what is this bearing, where is it located, where is this crankshaft, etc. It's impossible for you to know everything about what is going on. But within the first couple of days of your working, if you spend time, you will come to know the setup. Then it fails because now you go back to your basic principles. Everything fails when the load on that equipment is more than the allowed design limits. So then the attempt would be to pick that up, try to figure out what are the loads acting, and is there any chance that the loads sometimes become more than what was expected, and then if so, find a suitable measure. So that is the example of a automobile thing. The same example you can give, for electrical engineers, one of the common complaints is running equipment powered by a motor trips, it fails. Then, of course, the whole thing comes to a halt, and people come and complain to you saying that this motor has tripped. Now, what is the problem here is what was running was not running. Why it was not running? Then you will go through and find out whether it was an overload relay, or if there is any upstream fuse, or if there is an earth fault that has caused the protective thing to fail. So there will be a lot of reasons for it to happen. Then you have to take the given situation there to find what is most probable cause, and then find a solution to that. Now, this kind of a thing is impossible. Believe me, it is impossible for any college, anywhere, to teach the students, because there are so many of them. I think maybe the small differences, if you take medical education, for instance, some of the students who go for medical college have a little advantage because they go to the clinic close by. There is a hospital where patients are streaming in every day. Senior doctors are treating them. As they are getting treated, the student can observe how when this man comes, in that 5, 10, 15 minutes of examination, the senior doctor is able to more or less make up his mind as to what could be his difficulty, or he will order one or two tests to get into details of what could be the basis, and then comes to the diagnosis and accordingly the treatment. Engineers, unfortunately, we don't have that most of the time. In some ways, because all said and done, even if there is, an American body, human body, an Indian human body, and a Chinese human body, by and large are the same, right? Genetic differences are there, but the kind of ailments are by and large common. So if you had seen in one context, it's much easier to teach. Whereas in engineering, you want everything to be different from your competitor. So the designs are purposely made differently. The format is different. So basic point is you have to take what you call as practical and then try to read your fundamentals. Finally, it will be only 6 or 7, 8, 9 reasons. You have to go able to knack of connecting the right one to right thing you have to find. That's the first one. If you are still want to have, of course, you can take my email ID from PALS. I'll be able to, to come out with a very specific problem. I can help you. But broadly, this answer. The second is, what are the benefits of applying theory to workplace problem? This is good. Then you retain your job. If you are only a visiting professor to a company, then the company wouldn't hold you on for too long, because in the companies, their goal is, like I said, ethically, legally, service the customer, sell him something, and make money. So all people who are recruited in the company and paid salaries are expected to fall in line and help the company. So that probably is very clear. I mean, is there any other way, or any other reason why we should be applying theory to workplace problem? Because then you will be able to solve the problem. Third question, how will be our theoretical knowledge help to lead our profession? This is first two is probably. The thing is, there is nothing called theory and there is nothing called practice. You must believe in this. It might appear to me right now. In fact, it appeared to me when I was a student in 1974. I used to think, oh my God, why is so much of things is being taught to me? When am I really going to go out in the life and then start working? Then I think again, a couple of my professors said that your life, working life, let's say is up to 65 years. You are 21. So you will get a stage of 40 years to do what you are wanting to do. Why don't you just spend time trying to summarize of all the previous generation of engineers, what they have learned, they have codified into some knowledge, which is principles, applications, heat transfer, mass transfer, diffusion, kinetics, stress, and so on. So theoretical knowledge and practical knowledge are not very different. Theoretical knowledge is simply somebody has observed it, found some connection, and given you in a capsule. You have to remember that capsule and at the right time be able to pull out the right one and then start using it to your specific situation on that. So that is the larger picture. Question 4 is how the career will be for EIE department after passing out. I honestly do not know what is EIE. Is it
instrumentation engineering, sir?
Instrumentation. Electrical and instrumentation.
Yes.
It's very, 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 very promising. Like all disciplines. Because if you just say, you understand what is being taught in instrumentation and electricity is, how do you measure stuff? How do you measure and control stuff? That's the essence of instrumentation, right? Something you are trying to measure all the time, so that after measuring it, you will probably try to control it better. Take a very simple example. You know, as we grow older, people go and check their blood pressure. There is this push thing that is being used, doctor measures, and then if you find things are not going right, then you take a prescribed medicine for that, or exercise, or you change your diet or whatever. So designing sensors, putting together sensors so that they can communicate and transfer that information, and also connecting sensors to final control devices where based on that information that you collect, some logic, which is basically hardcore engineering, is used to control to the desired thing, is the big need. Because continuously the automation is increasing everywhere. You know, everything for the quality purposes, for safety purposes, for cost purposes. In the olden days, if you had hired an operator to watch the process and then take corrective action, you would still have the operator, I'm sure. You will not do away with the operator, but you will equip the operator with a large number of tools for him to better measure stuff, understand, and take corrective action. So the instrumentation engineering industry is most desired. The core companies really love it, excepting I think there is some tendency these days in colleges to go very esoteric. People talk about graphene-based sensors and things like that. That probably will happen up to 15 to 20 years time, whereas you are keen in the next 5 years, 4 years, what is going to happen. So the conventional instruments which are working to understand their principles, to be able to troubleshoot them, to be able to sort of even reduce the cost by strategically positioning, it's a phenomenally interesting and rewarding career. Chemical companies, manufacturing companies, all of them all the time are looking for somebody who as part of the team member on that. So it's a very promising career. The last is, can you implement this concept in mathematical based concept? I honestly don't know what it means. Whoever is written the question, can you explain to me what you mean by that? I'm not able to figure it out. Are you saying why is so much of mathematics in colleges? Is that the question?
Maybe he's asking if mathematical concepts can be applied to science, which is done left, right, and center all the time.
Yeah, I mean, so long as you know,
So supposing you're able to translate a concept into a mathematical equation or expression, then you will have a better idea of what to control, right?
yeah, possibly. See, I mean, it would be helpful with one concept. The easiest of the concepts all of us are taught. Take heat conduction, right? Heat conduction, when you start through solids, initially you will start with the definition of what is heat flux, which we say heat energy in terms of joules per unit area per time. So if you take that as joules per second per meter square as the heat flux, if it has to go from a higher temperature to a lower temperature heat, then we relate it by means of the famous equation, which is minus k dt by dx in one direction is equal to q in that direction. So this is a mathematical concept. Suddenly, some from nowhere, differential dt by dx dropped in. What it basically says is heat flows from a higher temperature to a lower temperature, and the quantity of heat flux is proportional to the temperature difference and inversely proportional to the distance between the two. So if you have two phases very far apart from each other, then the heat will flow at a smaller rate. So when means dx goes to the denominator. If there is a very large temperature difference between the two, heat flows at a faster rate. dt, which is the differential temperature, goes to the top. Now, at 8th standard, if you told, you would have simply said the differential delta T divided by L, they would have given. Simple, serves the purpose. You can imagine a slab. The slab has a certain thickness. It has a one phase hot, another phase cold. You can explain the same thing to the 8th standard student. He has understood the concept. But when we go higher, we use this Q of x is equal to minus k dt by dx. And actually, the full Hamiltonian is in 3 dimensions. Because if you are wanting to deal with multiple layers, very thin layers, and time dependent and anisotropic substances, where the properties of K, thermal conductivity, can also change along the length, then you are stuck with a differential equation. So a differential equation gives you a very general description, but the mathematics is incidental. The concept is going back to basic principles. So sometimes it is possible to express good concepts mathematically. Sometimes it is not. But at least you will get a heuristic knowledge about how it happens. That is what is more real. So yes, some of the concepts are possible to be converted to mathematical tools, depending on the situation. Yes. I'm not sure I give you a satisfactory answer because I'm not clear about what the intent was. So I'm very keen to answer you if I knew exactly what was in your mind. So you can just probably elaborate or write this.
Yeah, they can reach you at IRO at
wmail.iatm.ac.in.
Okay.
These are the questions we have received earlier, sir. Students or faculty, if you have any questions, please raise your hand. We have 1 more minute. Over to you, Anuman.
I find quite a few faculty also attentively being part of this session. I'm very thankful to them for being there. I saw Mr. Nagapan of Savita, so Parimala of KIT, I think, and Annette of Dr. Annette of MAMSET, and several others whom I couldn't recognize. But thank you all, faculty, for being there, and all the students, 121 of you who have been there for most of the event, most of the time. And I'm sure you would have got some insights into what happens in the industry and how you actually apply what you have read in classrooms or just mathematical equations, how they come to life in real life. So I'm extremely thankful to Dr. Mr. M.S. SRINIVASAN for sharing his knowledge and also giving the ways in which you have to apply your knowledge in real life. Thank you very much, sir. And thank you, PMO, Lavana and Robin, for being there right through. Wish you
Thank
all
you.
the best. Wish you all the best. This being the last T2P lecture for this year. I wish you all the best and see you all next year, the next T2P lecture. Thank you.
Thank you.
Thank you so much, Hanuman. Once again, I would like to thank Mr. Srinivasan sir for his excellent session. Participants, I hope all of you had a wonderful session today. I have posted the online quiz link and feedback link in the chat box. Quiz is based on today's lecture and some other general questions. It will be open for the next 24 hours. Requesting all the students to take it up. Best performer will get prize and certificate at the end of this academic year. And also, please submit your valuable feedback in the given link for continuous improvement. Thank you all. Thank you so much for the participation. Thank you, Srinivasan sir.
Thank you. Good luck, everybody.
Thank you, sir. Thank you, Robin sir. Thank you, Mani sir. Thank you, Anu ma'am. Ma'am, you are muted.
You can wait for 2 minutes
Sure,
and
sure.
then
We'll wind up.
Because
Sure, Anu ma'am. I lost you for a minute, actually. Thank you,
see,
ma'am.
because I was connecting to mobile data, I
Yeah,
lost
yeah.
it, and then I had to come in, and I wasn't co-host.
Good.
Keep quiet. So, good for
Okay.
you.
Just notice that at the end only. Once again, requesting participants, please submit your valuable feedback in the given meeting.